Great. So, so we have the pleasure to welcome Francesco Bronzino. So in these talks, usually speakers present themselves. So I'll let you present yourself. I just spent one word saying that, I mean, we talk a lot about machine learning in networks, but sometimes we do it with small data sets, with hypothetical models, etc. While Francesco did an impressive work on machine learning in real networks from and implemented all the chain from data collection to model training and prediction. So I'll give the floor to Francesco. Thank you, Francesco.
Thank you. I mean, we're still not connected to the team. No, yes, we are. Awesome. We're getting there. Okay. Let me just make sure that this is the right talk. Yes, it is. Cool. You should be seeing my screen now.
Yes,
Awesome.
perfect.
So thanks a lot, Andrea, for the introduction. I will very briefly introduce myself. I've been a member of Links for 2 years, plus the time I was a postdoc, so hopefully most of you remember my face. But anyway, I'm Francesco. I'm a maître de conférence at Université Savoie. And it's my privilege, I mean, my honor to get to do the last talk in Plus Italy for Links. After I spent like a number of years here, so I'm very happy to do that. Today I will give you a little bit of an extended preview of this work that I will be presenting next month at Sigmetrics. And in particular, this work looks at how the relationship that there exists between the models that we develop for managing networks, for network management, and not only the performance that they have, that they produce, but also about the costs that they imply. So the relationship to the constraints that there exist when deploying these models in real world networks. Okay, so machine learning networks, and as Andrea said, it's actually something that we have been increasingly been adopting, implementing, using for different type of problems. Network security folks were actually the very first ones that started using these tools extensively. We can see examples such as solving tasks such as intrusion detection, malware detection, so on and so forth. But we have seen that like these type of approaches have been adopted across a number of different types of tasks, more classical networking tasks, such as packet classification, inference of application quality from traffic or encrypted traffic in general, all the way down to even implementing routing itself using machine learning. What all these tasks and all these problems had in common is that all the solutions that the authors of these course had to develop had to take into consideration how we can present the information that we collect from network traffic, that we collect from the network using our measurement systems, how to present this information to the models, what we call the representations of traffic for machine learning models. So I didn't touch anything, I promise.
The problem is also online, so we see black screen.
There is no more TV. Are they cutting off the power of the building?
Online, if it's like online, it's not the TV. It's a computer. The TV is working perfectly. If it's online.
Yeah, I see the mouse actually. Yeah.
Wow.
It's a Mac issue.
Let's go back to it.
Can you share again your screen maybe, because
Yes. Sorry. This is a cursed presentation. Okay, we're back into the presentation. So let's get a little bit more into the detail about what a data representation for networking is and where it stands in the machine learning pipeline. The machine learning pipeline for network management is very similar to the way that we normally implement pipelines for machine learning. So the classical 5 steps, going from data collection to data cleaning, feature engineering, and then the creation of the models themselves. What makes this pipeline rather unique for the networking context is what happens especially in the first 3 phases. And in particular, the decisions that we have to take on how we go from the very rawest form of the information that we have in networks, so packets, the packets that are flowing inside the network, transforming these packets, first collecting them either in the form of packet traces or in the form of some statistics calculated out of that, and transforming over time to take a decision on how we present these statistics, these transformations that we created to the models themselves. More in practice, if we look at a graphical representation of what I just said, we have the packets flowing in the network. We have some measurement system that captures these packets, transforms them in some way to calculate the statistics and create the representations that we present to the models. For the sake of this talk, I'm grouping representations into 3 categories. I could do a more fine grade or more coarse grain classification, but just to give a number of examples, we can have representations such as aggregations and sampling, which are the most typical for network measurement platforms. We can see the most typical example of the most classical, actually, network representation, the one that is commonly available from measurement systems, throughput, so the amount of data that is flowing through a link. And all these representations are normally based on just some form of aggregating the amount of data or the amount of packets that are flowing through a link and calculating some statistic. Other types of representations are the ones that are based on events. So for example, we can keep track of how protocols behave. Example, a connection request between a client and a server. We can keep track of these events and create some representations like time series. Finally, we have seen a trend of new types of representations being created by researchers to improve how models perform. And one sort of cute one that I wanted to show as an example is the following one, where in some research work, what the authors did was to think the problem in the following way. They thought, okay, we know that machine learning works very well with images. What if we transform packets into images? And maybe the models will work better. And that's exactly what they did. They took a number of packets, they aligned their bytes, and they created grayscale images out of this. What all these representations have in common is that they can impact how models behave and perform. But not only across the most common way we sort of evaluate these models, which is the performance or the accuracy, but also across other dimensions. Let me show you an example of what I mean. Here I have the results of some models that we had created over the past. These models, doesn't matter exactly what they're doing. The purpose of me showing you this picture is that we can see that there are 3 models in the graph. And on the y-axis, we have their performance, their accuracy in particular. And on the x-axis, I'm just grouping them based on the representations they're using. The first model is using some classical network representation, think throughput, as I said. The one in the middle is using that plus some application-specific one. And the last model is using a large number of features. We'll see in detail later what I mean by this large, but you can think of is using these first groups of features plus some extra ones. So if you look at the plot, if I'm presenting the plot in the following way, you could easily interpret it by saying, well, the model I want to use in my network is the one using all the features. That's the one that is performing the best, is achieving the best performance, even if I'm doing that by just a little margin. If I actually introduce a new axis to the same figure, so the models are the same, the circle, the diamond, and the triangle and diamond are representing exactly the same models as before. But on the x-axis, I also plot the cost of each model, in particular, the cost in terms of how much memory my measurement system needs to use to collect the statistics that I'm using as input to my model. We can see that actually we might start to interpreting this plot slightly differently, and that's because it is true that the model using all features has a better performance. The thing is that this added performance comes at 2 orders of magnitude increased cost. So that's where we started this work, and we started thinking of, can we build a way for understanding the relationship that there exists between the performance of the models that we aim to design, we want to design, and we aim to use in the networks, but also taking into consideration the constraints of the systems that will actually have to use these models to generate the data that is used by these models. Actually, there are many factors that can impact the usability of a model in a network. And in this work, we're focusing in particular on the cost of collecting and storing the features. So how we go from the packets, as I said before, all the way to the input data that is used for the models. But there are many other things that we could be considering, like what's the impact of these features that these representations have on the execution time of the model, if I'm particularly caring for real-time execution. We could look at energy consumption. We could look at how well a model transfer across different networks. There are many different issues that we could be looking at. It's a wide space. And in particular, I like particularly how this paper that was presented by some Google researchers look at this specific problem. They call this type of cost, this type of considerations that come along with using machine learning in systems, the hidden technical depth of machine learning systems. This paper was actually published in the software engineering community. So it's not a networking paper, but actually aligned very well with the work that we were doing. And that's why I wanted to share it, because this work in particular is trying to explore, and this project more at large, what are the trade-offs, what are the costs, even implied costs that there exist for using machine learning in networks. So now I talked a little bit about like this problem of the representations. Let's get into more details about how we approach the problem. This actual work stemmed out of a previous work that we had done on how to infer the quality of video streaming applications from network traffic. Something that we had learned in the project was that representations did matter in terms of how, in terms of the performance that we could achieve with our models, the models that we wanted to develop for that specific purpose. And in particular, these are actually the same sort of like acronyms that I was using in the previous plot. So you can start guessing what models I was using back then. But what we discovered in that paper was that actually just sticking to the network representations that are commonly available from network measurement systems will have actually limited our ability to produce the models with the highest possible accuracy that we were interested in creating. So basically, everything that exists in the shaded area in the top right corner of this precision and recall plot could not be achieved if we just stick to the classical measurements that are available from measurement systems. Something that we could call, something that we could imagine is something that is produced by a system like NetFlow, which is typically used in the context of networks. So we knew that we want to be able, as network researchers, to understand what exists in the top right corner, but we also understood that there were many challenges in exploring this shaded area. And in particular, two major challenges. The first one is that we had done an extensive work as part of the project in collecting network traces. And the beautiful thing about having network traces is that they give you a complete freedom of exploring all the possible representations that you might want to create from this network traffic. But this freedom comes at a cost. Actually, two possible problems. The first one is what you're seeing in the plot in the bottom right, which is that collecting traces is actually fairly expensive in terms of storage. This is actually the difference in terms of like how much data you're generating if you're collecting traces, so pickups, versus if you're collecting just NetFlow data. You can see that it actually explodes exponentially compared to something that is mostly linear over time for NetFlow. This is a problem because network traces are great, but they are limited to the environments where you're collecting them, and that was actually true for the context of our problems. We've done a great work to be able to execute these models in home networks, but as soon as we try to execute the same models inside, say, a campus network in a university, these will break off because the models had learned to look at some networking conditions that were very specific to the dataset. So one solution could have been in that context to just collect more network traces from the campus network itself. But when do you stop? Like how much network traces, how much storage space you can dedicate to this type of problem? The second issue that they have is that, well, network traces are great, but they're recorded, they're offline. So you basically lose all the insights that you can gain from collecting data directly from a network measurement system. All the ability of understanding whether collecting these features is actually feasible or not in reality. So with all these, with these challenges and all these problems in mind, that's when we started working on Traffic Refinery, which is Traffic Refinery is a system that aims to enable the joint exploration of the relationship that there exists between cost and performance for machine learning models. Doing that means that we want to be able to provide a way for researchers and operators to create their models in such a way that they can target the models that both satisfy the type of performance that they desire to achieve, but that also look at what are the cost constraints that there exist in their network. So deploying a system that collects the features in a very flexible way, so they can define whichever feature they want to collect, whichever representation, but also get a sense of whether collecting this type of statistic is feasible in the network where they want to deploy their measurement systems. There were actually a number of challenges in doing this. In particular, we identified 3 challenges. The first one is that, well, we said that we want to have flexibility. We want to explore that blue shaded area. So we wanted to give as much flexibility for the model designers to be able to sort of like create all possible representations that they might think of without having too many constraints. So have a system that they could very quickly and easily just extend and be able to collect whichever features they wanted. A second challenge is that I said that you want to deploy this system in their network. So you have to find a sweet spot between give them flexibility, but still be able to deploy this collection system in a network where we could have very high speeds in the form of like gigabits and gigabits of traffic per second. And finally, we want to do all these while also providing a way to profile what is the cost of collecting these features. And this is hopefully, I mean, this is what we targeted with Traffic Refinery. And there are basically three main components, three main design choices that we had to take to develop the system and achieve these goals. And I'll sort of walk you through all of them in the next few slides. So the first thing is how we enable the flexibility that we wanted for the users of the system. So the idea is that when you take Traffic Refinery, start implementing the collection pipeline, how you collect the representations for traffic, you define a number of services that you want to collect traffic for. So here in the example, I have a service, for example, for Netflix, an application for Netflix. For this service, you define the domains, you define the rules for which that define which flows you want to collect statistics for. These rules are mostly based on domain names and IP addresses or patterns in the domain names. And then you specify the list of features that you want to collect. These features can go from classical ones, like I want to collect average throughput over time for this flow, all the way to, and with network representations, we are also offering sort of like a packet of available features that can be collected directly with the system. But the system can also be extended very easily to implement new features that will not be available. So the idea is that you can quickly just say, oh, I want to collect video segments for doing video quality inference. You just open your favorite editor. You have to implement two functions. Here I have like a tiny example. If you can see, probably you're too far here, but maybe at home they can see it better. But you basically just have to implement two functions. These two functions basically allow you to, or better, they require you to define how to process each packet, or better, what to extract, what information to extract from each packet, and then just provide a way to store the information that you calculated in some local cache. All the complexity that sits behind all the information, or all the structure of how this information is stored, is hidden to the user. It's really just about writing these two simple functions, and then write how to emit the data, how to output these statistics that are collected. I'll give you more detail later of how this could be done. But the idea is that once you have written this single file, you just copy it into the file structure of the system, and everything works automatically. The system uses something that is called language reflection, which is how programming languages learn about their own structure, to then learn what is available in terms of structures and objects. Basically, it handles everything for you. You just have to write these two functions, and then you can go and deploy your measurement system in the wild and collect statistics. In terms of real-time processing, we basically built a pipeline that is optimized to try to sort of support as fast speeds as possible. So the idea is that we want to minimize the amount of traffic that is has to be processed. So we are discarding all the flows that are not to be considered for collection. We are using all the type of like fast implementations, like zero copy implementations for collecting traffic rapidly, and we can support up to 10 gigabit per second collection without issues. The system actually supports both working in a deployment, so out of real traffic, but you can also, for test purposes, run it against recorded pickup traces and just sort of reevaluate what you have done, what you've implemented over unknown trace and environment. Finally, the built-in profiling. We support the profiling of 3 different cost metrics. The first cost metrics is the state. So we're measuring the amount of memory, the average amount of memory that flows for each flow that has to be used by the system to calculate the statistics for each feature in isolation. So the idea is you want to collect network counters, and the system will tell you, okay, on average for each flow, your system is using 2 megabytes for collecting that information. Similarly, we are supporting processing, which means that we are capturing what is the average packet processing time for each packet that is processed for calculating the statistics for this representation. And finally, also the storage, which is how much data has to be outputted by the system for each feature in isolation. And the idea is that all this is running inside the system. You don't really need to do anything in particular. It takes the same configuration. It's just a built-in feature that helps model designers to evaluate what they're collecting. So just very briefly, I'm not going to annoy you too much with the systems part. If you want to hear more about it, I'm happy to talk about it later. But the idea is that in the paper, we evaluated and demonstrated that the system can work at line rate on 10 gigabit traffic. We deployed the system inside a campus network in the US, a particularly noisy campus network with a lot of small packets being transmitted every second. And the idea is that in general, the system scales very well. In this case, we were testing it using a configuration to collect all the features required to do the video inference models that I briefly discussed about before. And in general, it supports the 10 gigabit per second without issues. What we observe is that there are only some issues when a lot of new flows arrive. This was particularly true for this specific network because this is a network sort of like a university network where there are also a bunch of systems for research that are running on. And we will see a lot of new flows every second being generated. And these spikes correspond to these specific scenarios where if we will see almost 150,000 new flows a second, no, actually over a 10-second window, that's when the system will start dropping. But 150,000 new flows is not the common scenario for every network. So we're fairly confident that this is sufficient to claim that 10 gigabit speeds are actually achievable. Even more interestingly, we developed 2 use cases to sort of demonstrate what the system can bring to model designers when developing the models. So what we did was taking 2 different types of models that already existed in the literature, develop them inside Traffic Refinery, and deploy them both using pre-recorded traces and using the campus deployment that I discussed before. And the idea was to sort of study what was the relationship between the performance that these models generated and the cost that will come attached with them. I'll start first from the video quality inference use case. So as I said, these were models that we had actually worked on. And during, and these models were basically using a collection of standard features collected from the network layer. So packet counts, throughput, the ones that I mentioned before. Some features that were collected looking at the transport layer. So basically keeping track of the state of the transport layer and how it works to calculate statistics such as how many retransmissions, how many packet losses. Some statistics that were that are rather advanced and could be interesting for a quality inference type of model. And finally, some application layer features. Application layer features were not calculated by peeking into the traffic, but rather by looking at the patterns of how packets were exchanged between clients and servers, and using this information to isolate information about how video was being delivered to clients. If you know a little bit about how Dash works, this basically means looking at the sizes over time of the segments of video that are being delivered. Something interesting is that in our work, we define the transport layer features as costly, as something that you will not want to collect, because we know that doing transport state tracking in real time inside a network is rather complex, is rather costly, but we have not done any sort of evaluation of what we meant by costly. That's something that actually the reviewers even had pointed out. We were like, yeah, we understand, but it would be nice if you could demonstrate this. So first of all, we implemented the whole pipeline for collecting all these features in about 100 lines of Go code, which brings me to the fact that I forgot to say that the system is developed in code in Golang. So about doing what I described before, so defining the two functions that came at about 100 lines of code, an entire 2 years of my life working on models implemented into the system. What did we learn? Well, first thing that we learned was the plot that I showed you before. This is exactly the difference that the models that I was showing you, and in particular, the fact that we had validated that the models that only use the network layer and application layer features were almost equivalent, even so slightly less performant than the ones using all the features, so also the transport layer features, but that this slight decrease in terms of performance came at orders of magnitude less cost in terms of different features, different metrics. In particular, in this plot, I'm showing you the amount of memory in use by the system to collect these features. Storage results are actually very similar. In fact, a lot of times, storage and state are sort of aligned, even though I'll show you that that is not the case for example, the second use case. But in this case, basically, the amount of memory needed is pretty much the same as the amount of output data that we have. So storage and state follow the same trajectory. At the same time, we found out, and this was interesting because we had actually thought differently, that processing time is actually not much of a problem. You can process all of them, all of the different features in the same sort of order of magnitude of processing speeds. To give you a little bit more of context about what I'm talking about. So first of all, this is a CDF again. On the x-axis, I have the average packet processing time, as I said before. And now I've added on the vertically the limitations between the different speeds, the different networking speeds. So how many millions of packets per second you need to process to be able to for your system to work at 40 gigabit per second, 10 gigabit per second, 1 gigabit. And the idea is that if our system works at 10 gigabit, it is capable of processing all these features because the average time it takes is less than what it takes to get the minimum per packet processing time to be able to support 10 gigabit. It doesn't get to 40. It doesn't get to 40 for any of them, which is not a problem because the system is not built to work at those type of speeds. It was actually a prototype. We could do many improvements to actually get to 40, starting from possibly not using Go, but moving to something like Rust, for example. But in general, this is what we were targeting for. But ideally, for this, processing is actually not a bottleneck. The second use case is actually interesting because it shows different types of trade-offs. And in particular, we implemented what I discussed about before, which is the using a deep learning model based on images. So using packet transformations into an image to perform malware detection. Just to give you like a super brief idea of how this transformation works, the idea is that you take packets, you align them into an array, choosing which parts of the packet to use. It can be headers, it can be payload. And then this array is converted into a PNG image. Again, we implemented this use case in about like 150 lines of code, the entire pipeline to also transform the data into the PNG. And in the paper, we discussed different results, but this is actually the most interesting takeaway. The idea is that here we are comparing different deployment strategies. And in particular, what happens if you, and this is like the full dot, just do in the system the byte alignment and collection to a byte array and just export that out of the system, which with the assumption that this byte array will be transformed into an image somewhere remotely where the model is executed. Conversely, the empty dots correspond to the deployment choice of actually doing the transformation on the system itself. What's interesting about this plot, which shows the median processing time on the x-axis and the average storage used by the system on the y-axis, is that actually depending on where you do what, you can have gains and and other attached costs for your system. So, for example, if you are processing limited, so your system is overloaded, say it has to process too many packets, you might actually want to avoid doing the transformation on your system and just export the raw bytes because it's actually very fast to do that. I mean, it's just a memory copy, so it's very easy. But if your system is actually more limited in terms of how much data you want to export, doing the PNG transformation on the system is orders of magnitude more costly in terms of processing time, but it's actually convenient in terms of how much storage you export. And that's due to how encoding in PNG works and the fact that a lot of the headers that you're using actually replicate the same information over and over and over. So encoding will actually capture that and reduce the amount of storage that you're exporting. You're basically compressing your information. And the idea is that this type of study can show what are the trade-offs between the different deployment strategies that you can take. Okay, so with this, I come to the conclusions. Just to sum up, we design and develop this system that enables the joint exploration of cost and performance for machine learning networking models. And we try to demonstrate that this actual exploration is important and should be taken into consideration as part of our quest towards solving the issues that are due to the hidden technical depth of machine learning. And we work with these two use cases to demonstrate that designers can take meaningful choices, and the choices they take can impact how their systems and models work on different deployments. This is actually a first step in some sense towards all the work that could be done within this space. Something to consider, for example, is, as I said at the beginning, broader range of costs. We only focus on three. I could mention like energy consumption or model execution time. All these are like different costs that are impacted by which representations we use. Another aspect that will be looked at in the future is how to automate this process. Traffic Refinery is already pretty good at like helping doing this joint exploration, but a system like something that takes inspiration from something like AutoGluon to automatically explore this model space and give suggestions to the users might be very interesting. And finally, we only focus in this work, obviously, on software-based implementations. There is a lot of work going on in networking using hardware solutions like SmartNICs or similar. And obviously, the cost relationship changes if you're using dedicated hardware. So it might be interesting to understand and extend this type of work on these type of solutions. This, I conclude, the system is actually open source. You can access it, you can use it. And as I said, the paper is already available and will be presented next month. And thanks a lot. Happy to take your questions.
Maybe a quick question about the data representation you presented last. Maybe PNP is just one compression mechanism. Maybe there are dozens of other compressions that could be more efficient and still preserve the ability to recognize.
Yes.
So Francesco, when you answered the question, can you please repeat it also, because online it was not audible.
Yes, I'll also put it closer, but yes. So basically, I was asked about the representation using the image and whether there are other ways to compress this data that are more efficient, or I mean, there are alternatives to this approach. Yes, there are. At the same time, it wasn't the purpose of our paper to explore the representations themselves and understand which ones work best. It was more about taking existing works and demonstrating that even within these works that were accepted by the community, there was a space, like a space that needed to be considered that was not previously considered in these papers. So we were not interested in like finding more efficient ways for compression. We just wanted to use what the authors of the paper used and show that something more could be done to take decisions about these models that were developed.
Yes.
Working on unidirectional or bidirectional traffic traces.
It is all bidirectional. I mean, this is all bidirectional. The recorded traces, the video ones, were recorded at INRIA when I was a postdoc there. So pretty much traces recorded from from behind an access point. The malware ones come from the, I think it's called IDS dataset, which is like super typical dataset for this type of problems. And we were basically implementing the same type of structure that I implemented in the campus network by using a network tab in a university campus, which basically means that all traffic will come to us, including bidirectional traffic. So
it was my follow-up question. So for tapping the network, you are basically copying the traffic without being in the middle of it, I suppose. So
correct. So you're not working in line. We were mirroring traffic out of it.
Okay. Other questions? I have maybe one.
There is another one in the room.
Oh, great. Please repeat it.
So when,
oh, yeah.
So when you compute some statistics, like you take so how much is the window that you take to compute some average statistics? So it changes over time. It depends on the user, like how much he wants or something like that.
Yeah. So basically, the question is like, what is the interval for computing statistics in the system? That's actually something that, no, it's in the other direction. Oops. I just get it. That's actually part of the configuration. It's not very visible from there, but the idea is that here there is a number which is 10, which is configurable. That's actually some sort of like one of the limitations of the system, to be fully honest, in the sense that the system is only capable of emitting at periodic intervals. So even for like event-based statistics you might want to generate, like say the connection request I was mentioning before, you still have to live within the constraints of the system, so do that periodically. But in terms of how frequently you can do it, you you could go down to less than a second or a minute. That's up to you. It's actually an interesting trade-off choice too, because the longer your interval is, the more state, for example, you might have to use to calculate the statistics. But the shorter it is, the more work the system has to do to emit it. So.
To me, like some kind of approximation theory, so similar to what the approximation theory was on. Example like mean field theories, like in mathematics. So you but use a tailored parameters, like a user will define like which parameters are his interest, and you do an approximation based on that user's interest. Because like, data is infinite and but the observer is finite, so you collect only the right approximation. And so there should be some kind of a tailor between like how much approximation you can do and how much your model truly represents what information that you want.
Yes. Okay. The question is very long, and I don't know how to summarize it, but I'll answer it. And if you didn't understand that, we actually do in the paper. It's part of the results I'm not showing. Some analysis about the relationship between window sizes and model performance for the video part, especially. And the trade-offs that there is, like what happens if you want to run, run models at 1 second versus 1 minute. And there is a relationship between how well your models work, aside for the cost, but also how well your models work, because, for example, video streaming behaves in certain ways. So the relationship between the information that you can collect if you just aggregate over a larger window of time and the behavior of this application impacts the type of inference you can do in it. We didn't do anything in terms of like how to automatically explore these relationships. It's something that the user should define and can define, say, I want to collect the same statistics, but at 5 different intervals, and then use this data to explore the models later.
Just follow up on this question. Out of curiosity, the best solution is 1 second rather than 1 minute for live streaming, I guess.
It's 10 seconds, and that's amazing because that's the one that we were using in the previous paper. I mean, our decision was actually based mostly on domain knowledge and how these video streaming applications work. The simple idea is normally video segments are either 2 or 4 seconds. So working at less than that, it's sort of not important because you're using less information than you can actually have for inferring the quality. While working at 10 gives you enough, for example, of like these video segments that are downloaded to average out enough information.
And it's kind of typical video cache for live events, for instance.
Yes. Yeah. But we have done it purely based on domain knowledge, and actually doing this exploration showed that it worked better than, say, we did basically 2, 4, 10, 30, 60. I think there are no more questions there. Andrea, if you...
Yes, maybe I have one question. So the complexities in terms of memory, storage, and computation are for collecting this data, no?
Correct.
And then you assume you get this data, you treat them offline, and then you have a model that is deployed, that is already trained, and you can deploy it in a real system. So, I mean, how can you then take into account also the complexity of the model? So you may have a model that is very good in terms of cost of collecting data, but then very costly in terms of doing inference on top of this data. So maybe it could be preferable to have a model a bit more heavy because it needs more data, but then the model itself is simple and so can do inference much faster. And have you observed this kind of trade-off, or it doesn't make any sense, or maybe yes, maybe not?
No, the comment makes a lot of sense, and that's sort of like part of the we didn't explore all the possible costs comment that I made at the end. Execution time is something that is definitely relevant, especially if you are taking decisions in real time, because taking decisions, if you're waiting for the inference to happen, that means that your system is either idle or has to cache stuff while you're taking decisions. So that's a real issue. We did not explore that until now. I mean, until a few months ago, until we were working on this paper. But it's definitely interesting. And yes, we're more focusing about the part of like getting the input data to the system before to the model before the model is executed.
Okay, thank you.
A follow-up. What part of this system could be kind of parallelized to achieve, let's say, higher throughput and not depend on the single threaded speed of machine or like that?
So the system is already, I mean, I didn't get into the system itself so much, but it's already scaling
So this appears on the machine
with a number of cores available. It is using hashing to basically distribute across interfaces. And we are basically using a horizontally partitioned cache here to allow to sort of like minimize the amount of concurrency you can get for these flows. Now, probably there are like further optimizations that we could do in this specific part. We didn't really go beyond this. For example, we only focused on PF-ring, which works well at up to 10 gigabit, and then like doesn't go beyond. You could implement it on DPDK using Rust. That's already, you could already gain a lot of speed by doing this. So there is a lot that could be done by just exploring how to improve the system, because we were like sort of working on this larger problem of the exploration. We didn't want to spend as much time on just like doing more engineering on the system.
And one last question about the kind of presumption that you had before, which was that TCP and application relevant features would be costly to extract. Where did that come from?
Well, it comes from the fact that you have to keep track of the state of each connection. And if you have, 100K connections in parallel, that means that you basically have to have a buffer for all these connections to know the window size, how many packets of the window size have been delivered, how many might have been lost, so on. If you want to calculate statistics as inter-arrival time, you need sort of like a time series of all these packets. So these were the assumptions, and the processing time maybe was.
This looks very much like what you do when you have a flow cache. Basically, you have to generate state and keep state.
Yes.
So in a sense, it comes for free with all the work that you're doing to collecting, let's say, all the bits of state over time.
Yes, I mean, no one said that if you have a problem where that those statistics are helping you to improve the model performance by X, where X is big enough, it's not something that you might want to collect. Our observation was rather than to improve 1%, but at 2 orders of magnitude extra cost, that might be something that's too much. It's basically like, what's the cost for this 1%? And we wanted to basically give it a number, and then it's your decision. If you have like terabytes of memory and you want to just collect it, that's fine.
Okay, so if there are no any more questions, we are. It's 4 o'clock, so perfect timing. So thank you again, Francesco, for the interesting talk, and we hope to have you again at Links in Palaiseau this time.
Thank you.
Thank you. Stop recording.